And why this matters, we have to look at our local context here in the UAE. Approximately 88% of the UAE population are expatriates, with the South Asian diaspora, specifically from Pakistan and India, making up nearly 38% of all residents. In this multicultural environment, speakers rarely stick to one language. Instead, they code switch, blending Roman Urdu and English with a single sentence. For example, a user might post, "The weather is great, but traffic bahut buri hai." Standard NLP models, which are typically trained on pure English or pure Urdu, fail to process these mixed structures, creating a massive gap in social media monitoring and service industry feedback. The hurdle in the processing the data are twofold. First, there is the script gap. Former Urdu uses Nastaliq script, but on social media, users rely almost exclusively on Roman Urdu, using the English alphabet to write Urdu words. Second, there is the issue of non-standardized spelling, because there is no official dictionary for Roman Urdu. This creates a massive out-of-vocabulary problem for traditional models. Our project aims to see if a multilingual transformer, specifically distilled word, can move past these surface-level spelling differences to understand the underlying sentiment. We specifically chose sentiment analysis as a target task for three functional reasons. The complexity of sentiment. Sentiment is rarely contained in just one word. It is often distributed across the language boundary. To know if a sentence is positive or negative, the model must understand how the English bridge connects to the Urdu descriptor. Data availability. Unlike other code switch tasks, we were able to leverage existing dataset like corpus, giving us enough data to actually test transfer learning. Now, measurability. It provides us with clear objective metrics. By using F1 score and accuracy, we can precisely measure how much knowledge is being transferred from the pre-trained model to the specific low-resource dialect. So now the question is, why transfer learning? Well, training a model from scratch was infeasible for three main reasons. Data scarcity. Publicly available labeled code switch datasets often contain fewer than 500 samples, which is not enough to train a transformer from random initialization. Large-scale multilingual transformer require billions of tokens for effective pre-training. When coming to resources, the computational and financial costs of pre-training exceed typical academic budgets for this project. So instead, we use transfer learning with Distilbird, which is already pre-trained on 104 languages, including Urdu. Methodology followed a rigorous four-step pipeline. The data pre-processing, we implemented custom normalization to standardize normal Urdu spelling and handle the transition between Urdu and Roman script. In the model selection, we used Distilbird-based multilingual for its balance, speed, and high performance. The training strategy was that we compare full fine-tuning, which updates all the 134 million parameters, against lower PEF, which updates less than 0.6% of the weight.
I'm Mariam, and I'm going to be talking about the dataset and the pre-processing. To get a good variety of data, we actually combined three different datasets. We used the Urdu sentiment corpus for traditional script, the Roman Urdu dataset for social media posts, and then the Daraz reviews to see how people actually talk in real world. After we cleaned everything up and got rid of any duplicates, we had a total of 15,309 samples. It was a pretty fair split too. About 56% of the posts are positive and 44% are negative, so the model had a good amount to learn from. For the pre-processing, before we could even think about the AI part, we had to fix our labels. Since we combined three different datasets, some used words like neutral and dislike, while others used numbers. So we simplified everything into two categories, which was positive and negative. We turned them into ones and zeros so the computer could understand them easily. Then we split our data into 80% for training and 20% for testing. The hardest part was that people on social media don't follow grammar rules. In Urdu, especially Roman Urdu, people spell words however they want, like spelling vary as bohat and bohot. If we didn't fix this, the model would think they're two completely different words, which they're not. We used a normalizer to group those variations together so the model knows they mean the same thing. We also used a tool called regex to scrub the data clean. It automatically hunts for and deletes things that don't help with sentiment, like website links, hashtags, and mentions. So by stripping all that out, we left the data with just raw emotional words, which makes its job a lot easier.
So for our base model, we went with Distilbert-based multilingual case. The reason we picked this model specifically is because it gives us the best of both worlds. It's 40% smaller and 60% faster than the original BERT model, but still keeps about 97% of its language understanding ability. In terms of architecture, it has 134 million parameters across 6 transformer layers with 768 hidden dimensions and 12 attention heads. What made it ideal for our project is the multilingual pre-training. It was trained on 104 languages using mass language modeling, and Urdu was one of them. So it already has some understanding of our target language before we even start fine-tuning. For tokenization, it uses a word piece vocabulary, which can handle both the Urdu script and Roman Urdu directly. No custom tokenizer needed. And finally, we attach a simple linear classification head on top of the CLS token, mapping 768 dimensions down to two classes, which is positive and negative. For the PyTorch framework, we implemented two test strategies. First, full fine-tuning updates all 134 million parameters of the model. We used AdamW with a warm-up scheduler and gradient clipping to keep training stable. Since our dataset is slightly imbalanced, 56% positive and 44% negative, we used class-weighted loss, so the model doesn't just favor the majority class, and we ran for 4 epochs. Second is LoRa, which takes a completely different approach. Instead of updating the whole model, we freeze the base and only train tiny low-rank adapter matrix injected into the attention layers. That's just 0.81 million parameters, which is less than 1% of the model, while the other 133 million stay completely frozen, and we ran the same 4 epochs and with the same loss function. Looking at the result,
For a Hugging Face implementation, we use the trainer API to simplify and standardize the training pipeline while keeping it consistent with our PyTorch setup. Starting with the full fine-tuning, the entire model was updated, meaning that all 136 million parameter was trained with an effective batch size. For the LoRa Perfect approach, instead of updating the full model, we froze the base model and only trained a small low-rank adapter layer. We used a rank of 8 and an alpha of 16, applied it to the attention layer across all 6 transformer blocks. This reduced the number of trainable parameters to around 0.81 millions, which is less than 1% of the full model. In terms of results, full fine-tuning achieved the best performance with around 79% accuracy and an F1 score of 0.81. However, LoRa performed very closely, achieving about 76% accuracy and F1 score nearly of 0.79, while using significantly fewer parameters. This shows that LoRa retains around 96% of the full model's performance while being much more efficient, training in about 11.5 minutes compared to the 10 hours for the full fine-tuning. Overall, this highlights the trade-off between the performance and computational cost.
Hello, I'm Roshni. So here we compare performance across 4 configurations. The best accuracy is achieved by 79.4% using Hugging Face full fine-tuning with an FN score of 0.814, showing strong overall balance. With LoRa, approaches are more parameter efficient, up to 168 times smaller. They slightly underperform in accuracy and FN score. This shows a key trade-off. Full fine-tuning gives better performance, while LoRa is faster and more efficient but less accurate. This slide evaluates how well the models understand culturally specific Urdu expressions using the CPC score. PyTorch full fine-tuning performs best at 81.8%, followed closely by PyTorch LoRa at 78.2%. However, Hugging Face LoRa drops significantly to 58.1%, indicating difficulty in capturing cultural nuance. Key insight here is that LoRa models struggle more with culturally rich language, which is not always reflected in standard accuracy matrices. So here, multi-language, they still work, successfully transferred knowledge across Urdu and Roman Urdu. However, LoRa methods underperform compared to full fine-tuning, especially on culturally sensitive data. This is mainly due to domain shift from formal training to informal social media and the limited adaptability of parameter-efficient methods. Overall, LoRa is efficient, but full fine-tuning remains more reliable for nuanced language understanding. Thank you.
And I'll explain you the code repository of our project. So as you can see, it's pretty clean here. We only have 2 notebooks mainly. So this one is Urdu PyTorch and Urdu Hugging Face. This shows implementation of distributed model for both the frameworks. For the PyTorch model, this one is more hands-on. We have a custom training loop defined here. So after loading the dataset, labeled standardization, combining all 3 datasets and visualizing the dataset, seeing the class imbalance in the positive and negative classes, we are doing the pre-processing here, and the rules are defined for the Urdu script and Roman Urdu separately. And then we also have tokenization down here, and then the training loop here have been ramped. And then these are the class weights as well as the learning rate defined here, and then the evaluation functions also defined. For the first strategy, full fine tuning, we have 4 epochs and the learning rate is 2e-5. This is a report, classification report after doing the training. And then for the second strategy, low rank adaptations, we have applied it for distilled attention modules mentioned in here. And then it uses basically 0.6% of the total 136 million parameters. These are more detailed evaluations on both the models and comparing different metrics for it. And then we also defined CPC score in here. We tested it against 55 phrases for both the models and a qualitative inference testing as well. And then both the models are then saved to a deployment folder in here, deployment assets for PyTorch. Then for Hugging Face, this one is more high level since it uses a trainer API, so it abstracts all those details we have done in the custom loop in the PyTorch. So again, after combining the datasets, pre-processing it, we have used a regex space cleaner in here, which will do it in upfront, so before it even starts. And then after tokenization and defining the evaluation functions, we have used both training strategies, full fine-tuning and low rank adaptation, same as PyTorch. So then we have compared both the models, and again we have compared again in more detail, and then we both save both the models for deployment. We also have compared using the CPC score similarly in as PyTorch, and we have tested against 43 phases, and then we also have done quality inference testing, and then see the results in here. Now for the deployment, it exposes a fast API endpoint where we can send text and get predictions back. There are mainly 4 endpoints defined, including predictions from either a single model or from all models simultaneously. Then we have a Docker file in here. So it packages everything together so the whole system can run with one command. This is the Gradia UI. I have written a simple text called EHE's prehead, which basically means this thing is bad. And then I have pressed compare all models in here. So you can see basically all the key PyTorch models have predicted correctly, but you can see the Hugging Face models, it predicted it positive sometime. So you can see it shows a real challenge. So handling negation and a cultural context in a code switching language. So that's it. Laura struggled with culturally nuanced phrases and mixed sentiments, showing that parameter-efficient models still have limitations when deeper semantic understanding is required. So looking ahead, future work can explore larger multilingual models like Excel and Roberta. So it improves more cultural understanding using native Urdu input, and we can extend this approach to other languages such as Punjabi and Sindhi. Overall, this project highlights that both model design as well as the training infrastructure like PyTorch, Hugging Face, TensorFlow, and Keras displays a critical role in successful transfer learning. Thank you.